This is the very last section of chapter 16. So we've made it very far. You should be proud of yourselves. This is where we're going to do change of variables in multiple integrals. And I think the best way to introduce the concept is to actually invoke what you already kind of know about changing variables into integrals. We didn't really call it change of variables because when you took this originally in Calc 1 or Calc 2, depending on where you did Calc 1 and Calc 2, we just called it substitution method, right? And so if here's a classic example. So this is something you would have seen in Calc 1. Say you had integral 0 to 1 to the square root of 2x plus 1 dx, right? Something like that. And what we could do is we could say, okay, well, this is equal to the integral 1 to 3, the square root of u times du. And the reason why we could say this is because we're using the transformation u is equal to 2x plus 1. We call this a u substitution, but in reality, in the more general picture, this is a very, very simple case of change of variables. So here's a kind of the list of things that get changed, okay? So we're going to note there's a change in, changing. First kind of things that we're changing. Here we're going x is 0, x is 1. Here it's u is 1, u is 3. So we're changing the limits of integration. Limits of integration. The second thing we're changing is the obvious. The integrand is different. 2 times the square root of 2x plus 1 is different than just the square root of u. So we change the integrand. And when all of those things change, another thing is forced to change that gets hit under the radar, which is going to be very important today, is the differential. Dx turns into du when we switch variables. So we have the differential. Okay, so far so good, right? This is just review. And so we can also recall, and even though this isn't maybe Calc 1, this is technically something we've covered already in class, and we can invoke the memory of it. So if I had a double integral, say 0, 1, 0 times the square root of 1 minus x squared, and then the integrand is e to the 1 minus x squared minus y squared dy dx differential, is that if you were to transform this using our polar, because we know that anything involving the circles is best done not Cartesian, but in polar if it's circular. And we can say, oh, this is much simpler to do in polar if we express the region as 0 to pi halves on theta, and then the radius going 0 to 1 over an integrand of 1 minus r squared. And then in polar, what is the dA?
R d theta.
So then that's what the new differential is. R d theta. Okay, so do you see how these three changes are exactly the same, essentially in concept? Did we change the limits of integration? Yeah, we have 0 to 1, 0 to blah, and now it's just 0 to pi half, 0 to 1. More specifically, the region has been re-described. So over here in R, we're talking about some region R that we would describe in Cartesian as x, y, where x and y are greater than equal to 0, and then x squared plus y squared is less than equal to 1, right? Because we're taking that upper part of the circle. And so in rectangular, here's some region R. That's now, so the limits of integration in Calc 1 is just some interval on the real line. The limits of integration in Calc 2, like with the double integral, is going to actually be like a two-dimensional region. And so this limit of this region for the limits of integration gets transformed into a polar region, right? Some s with respect to the variables r and theta, because those are polar, into a much easier polar rectangle. 0 less than equal to r less than equal to 1, and then the theta gets swept out. 0 less than equal to theta, and then pi halves. So here, where we would say in u substitution, well, the 0 gets changed to 1 and the 1 gets changed to a 3. Here we would say that the input, this region that we're choosing to integrate over, if we do the proper transformations, it's going to look like that in polar, as a polar rectangle. Same concept though. It's still just addressing limits of integration. What else are we changing? We're changing the integrand. Integrand is e to the 1 minus x squared minus y squared. Well, under the transformation equations, right? So instead of just having u equals 2x plus 1, we need two equations. And those two equations is x is equal to r cosine theta and y is equal to r sine theta, something you're familiar with. Do you see how this is analogous in idea? These become those equations that we transform that integrand and substitute into when we get a new integrand. And then the differential, dy dx, this is what we mean by the dA. This is the expansion of the dA in Cartesian. And so then naturally our dA in polar, and that's like I asked you, what is the polar dA? Well, we already did. Okay. So when we do these change of variables, we are changing the limits of integration, we're changing the integrand and the differential. All three of those things need to look different when you're going to do this, and it's going to involve you all the different pieces. There is no method. That's what makes it a little bit more tricky. So what we're going to talk about is pretty much the only part of this that is methodical, because that's the only thing that's really fair to test on. But anyway, let's do. Is this good?
Yeah.
We good with this, so we can move to some examples of what we really talk about. I might be able to fit it on the bottom of this one. Actually, I'll do that. My family likes to have the most riveting conversations at 1 o'clock Central Standard Time.
Wait, Scott, I have a quick question.
Yeah.
For the limits of integration, if it was 0 to, let's say like 200, would it still be 0 to pi half in the integrand?
Are you talking about 0 to 200 rectangular? Yeah. Okay. So what this 0 to 1 is with the x's, right? So when we're looking, this is the region. So this is described as the iterated integral that describes this particular region. So if I were to change this 1 to a 200, you would also have to be forced to change with this numbers as well, because this is describing a radius. So this number 1 would actually need to be 4,000.
Just good.
Because it'd be then r squared minus x squared. And then the region would be described by x squared plus y squared is less than or equal to 200 as that new radius.
Okay.
And then that would get expressed over here because the radius is now 200. So then it'd be 0 less than or equal to the radius less than or equal to 200, which would be that radius. But theta would stay the same because that's just simply what we're choosing. We're just sweeping out the semicircle up top. And that's what this is. Top of a semicircle. Okay. Is that good?
Yep.
Cool. So the polar transformation, like we talked about, is x equals r cosine theta, y equals r sine theta. Do you remember what? So if we're talking spherical coordinates, then your x is what? How do you translate x over into spherical? Do you remember? Exactly. So the rho sine phi, think of rho sine phi as your r. That's kind of how I do that to minimize what I have to memorize. Is that r is, if I think in spherical, that's just rho sine phi. Then the theta stuff is actually parallel to what we see in polar. So it'll be rho sine phi cosine theta for the x, and so then that means y is going to be what?
Rho sine phi sine theta.
Exactly. We just use sine theta instead of cosine theta. And then z is going to be the one that's different from cylindrical, because we use trigonometry and say, oh, we're actually taking the cosine component of what the angle we dropped out. So then z changed it up and said, no, we're not going to use rho sine phi, we'll use cosine phi because it's the other side, the other ratio. Okay. And see. Here's the definition that's good to know. Because we'll talk about one-to-one, and this concept of one-to-one is very transcendent in general. You'll talk about it in algebra and set theory and everything, but you're engineer, so here it is. A transformation T from a region S to a region R. So as I write this definition out, the reason I put this example right next to it, so you can kind of see, we're transforming, well, in this case, we're doing R to S, but same difference, is 1-to-1, 1-to-1 on your region S, if if I tell you that transforming some point P gives you the same thing as transforming some point Q, the only way that that's possible is if P and Q are actually the same thing. Because they need to be unique pairs, right? P equals, yeah, where P and Q are points in S. Here's a more intuitive idea of one-to-one. Okay, so in monogamy, because we're not a polygamist, well, Utah is different, but basically, if say Axel, say you get married to someone, okay, and then in the event that we're looking at, okay, well, if Axel's wife is P and Axel's wife is Q, the only way that can be true if P is equal to Q, right? It's the same idea. Only one association. You can only pair one thing to one thing. You're not gonna have two things mapped onto one thing, or one thing going into two things. Okay, so it's going to be unique pairings, where you can know exactly the address or its relationship to one point just by nature of what it's been related to. Okay. So like a line is a perfect example of one-to-one. Every single point on a line is coming from an exact unique point in its input space. And so you can always relate, I just need to know the input. I know exactly what the output's going to correspond with. And you can even go backwards because it's one-to-one. I can say, even if I know just the output, I can still go backwards and find the input because I know that that relationship is one-to-one. Trig functions don't really do that because you can obtain lots of the same. You repeat one periodically or zero periodically for an infinite number of inputs. So that's an example that would not be one-to-one. Things like lines, some polynomials, exponentials, logarithms, those are one-to-one. Quadratics, are those one-to-one? No, why not?
That's one.
Yeah, so if I told you, hey, my parabola, it spit out the value 1. Well, which x value could have given that? Yeah, that could have been 1. 1 squared gives 1, but the issue is -1 squared also gives 1. So it's not unique. Just because you know what the output is doesn't mean you can identify for sure what the input is. That's what this is about. Is that if you had the line y is equal to x plus 1, if I said, hey, the output is 1, you can know for sure. You can trace that back and say, well, it comes from 0. Because 0 is the only value that 0 plus 1 gives 1. Transformations, sorry, what?
Just would a function if it was x cubed or something like that, so you could just x cubed if it was
Yes, specifically x cubed. You start adding other things to it and start adding in like some loops and stuff, you can get repetition. But yes, x cubed by itself will still be equal to 1. Because you can give me any cube and I can tell you exactly where that's coming from. And there's only one possible way for that. So what this means for regions in R2 is that every single one of these points x, y, or if they're saying S to R, I guess I'm dyslexic when I made my notes, but okay. But if you have a point going in the Cartesian space into a polar rectangular space, then each one of these is going to be paired with exactly one of these. We're not double counting and we're not double mapping anything. So every single point over here will have exactly one pair over here. You'll always be able to know what that is. And if I choose something over here, it's only going to correspond with only one over here. And so that's what we mean by a one-to-one transformation. These are the transformations we need for changing the variables. Because if we're going to say, I'm integrating over the same region, I better not be double counting on the same region. Because then I've just inherently changed the integral. And so that's why we're going to require this idea of one-to-one, especially extending to the idea of points and regions being paired with exactly only one point of region. Yeah.
So basically using the outer limit, the lower limit and the top limit of the integral point.
Yeah, kind of. So you'll use the given information in the iterated integral. Here's the path you'll take. You'll be given something like this, and you'll say, okay, pause. What region is that describing in this set of variables? Okay, now that I know what region I'm describing with that set of variables, is there an easier set of variables to do it? Polar deals with a semicircle far better than Cartesian does. So let's write it like that. And now that I've done this, I need to now re-express the equivalent idea with the new iterated integral. So take that line of reasoning. Is start with what they give you, then interpret what that region actually is, decide a good transformation for that region, and then rewrite in terms of that. Does that make sense? Okay. All right. right, so let's get on with the Jacobian, because the Jacobian is the main, that's like the main highlight of this last section. Is, if you thought U substitutions were complicated, oh boy. This is U sub on steroids in calculus. There's gonna be two versions, one for R2 and one for R3. The one for R3 looks really complicated. It's just an extension of the idea given in R2. So if you take the time to get to know the R2 situation, you'll be fine. It won't be anything much different. Considering I don't give or let you have formula sheets, I would definitely have these in your notes for the sake of memorizing for Monday, because guess what you have on Monday? And on Friday, we have exam reviewing in class. And then also on, we chose Saturday at 6, right? I have a piece of paper in my thing. We reserved this room so that we can kick people out if they're in here doing unholy things.
Also what on Friday.
Yes, we'll do stuff on Friday as well. Okay, definition. This is the big one. A big one because it's realistic enough for you to apply and it'll probably be in lots of the homework. And so given a transformation, and the way we say that, we'll talk about the transformation generally as T. We'll use the colon to say, hey, T is going to be the symbol we use to represent a transformation that will be defined and its definition follows these colons. Make sense? So T, in English, you can read it as T defined by and then its definition. So X, it will be transformed by some function of the new variables U and V that we're trying to get to. And Y will be expressed in terms of the new variables we're going into. So let's so given a transformation where we want to make sure G and H are differentiable. So are differentiable on a region of the UV plane. UV plane. The Jacobian determinant. Jacobian determinant. Ding ding ding, big important word. Jacobian. Sometimes we just refer to it by the Jacobian because this is implied, but the word determinant is going to kind of express the computation that you're going to do. T is, so we say the Jacobian UV. We'll do something kind of interesting. We've got two variables X and Y. We also trying to go into two variables U and V. So we're going to do this partial with X and Y, but then we also have partial for the two variables U and V. Okay. Determinant, that's basically what this is defined as. It's a very specific 2x2 determinant in this case. Up top is the x's, so it's going to go x's, y's. So the x's and the y's give the rows, the u's and the v's are going to give the columns. So it's going to be dx, du, dx, dv at the top. And the pattern continues because now we're just going to do the y's on the next row, but the order of the u and the v is still the same. So what's going to be the bottom row here?
dy du.
Right, partial y, partial v. Boom. And I trust you know how to take a 2x2 determinant by now. In general, I guess for the sake of having it on the whiteboard as a refresher, if you have the 2x2 determinant A, B, C, D like this, you compute that by taking the product of this diagonal and subtracting that diagonal. So AD minus B. So the A in this case happens to be a whole partial derivative, but that doesn't matter. The idea is the same. You'll figure out what these are, and then you'll times and then subtract the product of those. Okay. So it's nothing crazy. Hardest part about a Jacobian is just writing down your work, honestly, because when you're given the transformation, all you gotta do is compute your pieces. So before trying to throw everything into the determinant, just find out what the partial derivatives are in the first place. And then once you find what those are out in your scratch work, then just put it together. Better yet, you could actually just write out this product and then plug directly into the simplified product, so you don't even have to look at another matrix. Okay, so these aren't difficult if you are in the habit of showing your work. So don't get routine and doing stuff in your head, because when we expand this to 3 dimensions, it's just not going to be pretty. Especially when these get a little bit more complicated. That make sense? So commit this to memory, please. It's important. Okay. And then depending on how much time we have, when I get through the rest of the definitions, we might go through an example of this. But for now, you need to see how this works out when we actually rechange the integrals in the double integral. So here's our theorem. Let P as given by x is equal to g u v, and then y is equal to h u v as well. The transformation that maps a closed bounded region S in the UV plane to a region and we call R in the XY plane. And then we're going to assume that T is 1-to-1, because again, why do we need T to be 1-to-1? Well, if I'm double counting points, in other words, if I can't guarantee at a certain point when it's in S space goes over to the, or UV space goes over to XY space, if there's double copies, we've got an issue with my limits of integration. So this needs to be 1-to-1. So assume that T is 1-to-1 on the interior of S, and that your functions g and h have continuous first partial derivatives. First partial derivative. Okay. Just a word of why on earth theorems often have these massive annoying chunks of English before the math part. It's because it's important. I didn't realize until this semester why all of these things matter. But things like being closed and bounded in a certain plane. These are topological ideas that you can come to seminar if you want, Tuesday at noon, to learn all about these. But the idea is this stuff we can't take for granted. So things that we intuit about these regions are not necessarily obvious. So these caveats of why we need to specifically outline closed and bounded, and specifically outline the planes that we're going to, specifically saying we need to have 1-to-1, specifically saying we need the interior and not just S in general, needing continuous first partial derivatives because of how we're going to define the Jacobian. Everything has a place. There's never a not necessary thing in a theorem. A theorem is the preamble is going to be the minimum requirement of hypothesis statements you need in order to take advantage of the shortcut that's about to follow. Okay, so yes, I know this is tedious. You think I enjoy writing out all these English? No, I don't. But I recognize that it's important. Not just important, it's necessary. So it'd be wrong if I just wrote stuff down. You need to be aware of the hypothesis in the theorem so that you can appreciate then why we're able to use the result of it. Okay. Do you need to have this stuff memorized at this level? No. So don't do that because you're going to be given 1-to-1 transformations and you're going to be given closed bounded regions and you're going to be given differentiable things. But if you ever pursue master's level stuff, this kind of attention to detail, it becomes the norm, okay? So heads up for what would be coming. So then here we're gonna do one more condition. We need f to be continuous, which is gonna be the integrand. So if f is continuous on R, then at long last, we can change the variables. So there's a good old laundry list, a little bit more complicated than a U sub. But it's necessary. And then I'll just write it out on this bottom part here. So we can take some double integral that's been currently given in R over a region R with the variables x and y. And when we now change this into u and v, so this isn't a u sub anymore, it's a uv sub. We're changing double integral. The limits of integration are going to be given now in terms of S, which is now that subset of uv space instead of R subset of the xy space. And the integrand, so where f is, we need to change x under the transformation, where x is going to be whatever this function is in terms of u and v. So g of u and v. What's going to be the y coordinate? What's y going to turn into?
H of U and V.
Good. H of u and v. So there's our integrand. Here's the change of variable stuff. So you know how when you do the du equals blah 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 dx, right?
Yeah.
And so the stuff that's coming before that, the dx, is the magnitude of the Jacobian. So that's why we have the Jacobian. Is we compute whatever this is, and that's going to be essentially function. It's standing in the place of scaling the differential. And then dA is still on the outside. And the reason we talk about it generally in dA is because sometimes you won't always use the same kind of double integral stuff. So you might not always default to polar. You might default to a different change of variables that'll be better, or a different transformation that'll make your integration easier. Bottom line is, this comes from changing the x, y, dA. And then we can find that just through this computation. So there's a reason why we showed this separate from here. Because if I just showed you magnitude of the and plugged this entire thing into there, it'd be just horrible. And not very pretty to look at. So okay. So there's a lot of stuff on this whiteboard. I would say that this and this are probably the most important. Just because, yes, you can extend all of this to R3, but then the amount of time it takes to actually realistically do one of those problems, this goes up by like 250%. Because then you have to compute so many more derivatives, and the transformation takes a lot more time to do. But questions about what transformations are? Questions about why we're saying the notation colon and then the x is equal to a function, y is equal to a function. Okay, questions why we need these to be differentiable. Questions on notation of the Jacobian.
Why is it specified as a Jacobian if it's just the determinant of the 2x2 matrix? Because like earlier, that was a Hessian matrix, and now it's a Jacobian, and so.
Very big question. Well, we relabel things depending on the context as we go.
Sure.
For example, in continuity, I've been lied to so many times as I continued in pure mathematics. Continuity was, don't pick your pencil up. Then continuity said, because it looks like it. Then continuity was, well, if your limitless on the left and right approach the same thing and the function is also there, then it's continuous. But then continuity became, well, now you need for every single positive delta, some open set with a positive epsilon that it is. And then it became, well, no, that was all a lie. And actually, that's just a shadow of topological things. So if you have topological spaces being mapped into each other, then the open set in the range space Y needs its inverse image to be open in topology for X. And so I'm sure in 2 more years, I'm going to get a different definition. So the idea is we keep, we use these names and things to keep kind of contextualize the reason why we use certain things. And so I wouldn't answer some 8-year-old, who's saying, what's a continuous function? And I'm not going to tell them what epsilon delta is, because that's mean. And so the same reason, so Hessian matrix, I'm pretty sure, is the more general form of taking the 2x2 determinants or just n by n square the determinants for partial derivatives in general. But the Jacobian is going to be specifically the context of changing variables. So when you see your Jacobian, that's going to say, yes, you're doing the concept of Hessian matrix or Hessian term, but in the context of changing variables for either double or triple.
Oh, a new type of determinant. And then
Yeah.
Same thing.
So naming things and naming conventions have a lot more history going on, usually in their development and context of use. But that's a good question. Yeah. Okay, questions about actually how you would realistically memorize this discriminant? Again, X is on the row, so on the top, these are going to tell you what the rows are. So X is top row, Y is the next row. And then on the bottom, these are going to be the columns. Use these. So if I added another, if I made this 3 dimensions, well, it's just going to be all the X's on the row, Y row, Z row, and then U, V, W. Okay. Question about, are we good with what 1-to-1 is in general? Okay, Chelsea's like, this is too easy. I've taken linear algebra. I know more than you could ever want to know. Let's see. And then questions about the actual change. So R going to S, X, Y. Because you've already been doing that. That's the idea. Is technically speaking, ever since we started doing the other coordinate systems, we've been doing this. Now we're just getting a bigger picture of what's going on. The DA. So DA and polar is what?
R derivative beta.
R. We already did that, okay. In spherical, so we haven't done the triple integral yet, but when we do the same idea, spherical dV is what? So that little rho squared sine phi before all of the differentials. Okay, so it comes from somewhere. You can compute those things. All right. I think I said on was it Monday that we did the spherical stuff? At any rate, when we talked about the spherical coordinates, and I just wrote down rho squared sine phi, and then and everyone went, oh, and I said there was a reason for it that we would talk about later. There's the reason, because that's going to come from one of these Jacobians. So this is the 2x2 version. I'll write out the 3x3 version so you can see it. And I think I'll make some sort of a 3x3. Yeah, I think I might do like a 3x3 Jacobian or like a change of variable verification, like an extra credit problem. So maybe if I'm gonna do that though, I won't actually show you how to do it. Because the whole point of it being extra credit is figuring it out. But I will show you a 2-dimensional case. Okay, so what I'm gonna put up here is gonna be more oriented toward it's important. But it's gonna be definitely more if you're looking for an extra letter grade or something on an exam or something. Okay. So given a transformation. Okay, so T, we've given the name to our transformation, colon. I'm about to give its definition. We're gonna have 3 variables now, X, Y, and Z. So X we're gonna call G, and then the variables we're going into is U, V, W. So Y is some other function H, U, V, W, and Z. G, H, let's go to P, U, V, W. And where G, H, and P are differentiable. We need them to be differentiable, otherwise it's a problem. Differentiable on a region of the UVW plane. Okay. The Jacobian determinant of this. Jacobian or just the Jacobian again. You know, in jazz, they say repetition legitimizes. Mathematicians should have learned more from jazz musicians. Okay. So the Jacobian of T is J. Where do I want to put this? Gotta think of how much space I've got on the. Okay, I'll put it right here. J, U, V, and W is going to be so the variables that we're coming from are X, Y, and Z. What are the variables that we're trying to go into?
UVW.
Yeah, U. So, what are the dimensions of this determinant?
So 3 by 3.
Yeah, 3 by 3. Okay. If these are the rows and these are the columns, what is the first row going to be?
X.
Right.
Yeah.
So then I have partial X. Okay, great. And then what's that column?
U.
Good. Okay, what's going to be right next to it?
Partial.
B. What's going to be right here?
Partial Z.
X. Partial.
W. Great. Technically, if you memorize that top row, everything else is pretty much for free because you just got to copy and paste, copy and paste. So what's the middle row going to be?
Partial Y.
Partial
Partial
Y.
U.
All right, partial Y, partial U. What's this one?
Partial Y.
Partial Y.
Partial V.
V.
And then this one.
Partial Y. Partial W.
Bottom row.
Partial Z. Partial U.
Right. Then, so then just finish out the pattern. Now, we're gonna review how these three, well, actually, no, because this is the extra credit thing. I can't teach you that. We gotta figure it out. Okay, and then for the theorem, blah, 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 right? So we're gonna require the transformation to be on a closed bounded region in UVW space. We're gonna require the transformation to be 1-to-1. And we're gonna require L, the G, H, and the P to have continuous first partial derivatives for the Jacobian. And then we're also going to require an integrand function that in itself is continuous on the new region that you're integrating over. If that's all true, then, so blah, 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 then, because I refuse to waste more ink for all that English game, is we're gonna have the triple integral over that region D for the X, Y, and then dV. That's going to be equal to triple integral for this new region S. And the integrand, so what's going to be in the integrand? What do I put here?
G.
U, V, W. What's the next one?
H.
And the third one?
P.
Okay. In the same exact construction of the previous one, what do you think the ending of this is going to be?
P. Absolute value of the Jacobian.
So, in spherical coordinates, dV is what?
Rho squared sine C d rho d d theta.
Okay, everybody's tired. That's it. I'm tired too, but we can do better. Okay, spherical dV is what?
Rho squared sine P d rho d p d theta.
What's the Jacobian? What do we anticipate this magnitude of Jacobian here? Yeah, rho squared sine P. That's that. Coming from rectangular. Right? Okay. To answer your question, Diego, what is spherical dV? We'll continue on. Good. So if the d rho d phi d theta is contained in the dV here, and then this entire thing is now the new dV, essentially the rho squared sine phi, is what's going to come out. That's why it's rho squared sine phi. If you were to put the transformation equations of, okay, when spherical, in spherical, x is equal to what? Right, the rho sine phi cosine theta. So instead of this being u, v, and w, we would say this is rho, phi, and theta. With the relationship of rho sine phi cosine theta. The y has the variables you are rho, phi, and theta. But then under the relationship of rho sine phi sine theta. And then the last z is some function of rho, phi, and theta. Specifically though, being just the rho times cosine of phi. Ooh, you can throw that in there. We know what that's supposed to simplify to, okay? So here's gonna be what the extra credit question will be probably. I'll formalize this, I'll make a little PDF thing and I'll post it to the D2L shell. But so that you know what it's gonna generally be, it's going to be proof that spherical dv is rho squared sine phi, d rho dv d theta, from the Jacobian that transforms in R3 from xyz into rho phi and theta.
Wait, the proof is showing.
So show that if you define a transformation that specifically takes the rectangular coordinates into spherical coordinates, if you write down those transformation equations and actually go through the process of computing this Jacobian, you'll end up with the output of rho squared sine phi, which is why we know that that's what we multiply by. So it's not actually that difficult to do if you're patient enough to sit down with the determinant. Go through the exercise of doing it, okay? Because if you do, then you get extra credit. And everybody likes extra credit.
Is there possible on that extra credit?
Huh?
It's the partial extra credit.
We get everything.
Well, considering this is something you're doing on your own time and you can check it before you turn it into a Dropbox, I'd hope if you cared about your grade enough that you would proofread your work. Yes. Let's make it due on, okay, so you're taking your exam on Monday. So it will be due, ooh, this is how we'll do it. Okay, so you'll have a lab that's due the next Friday. So then add that file of your solution to the Dropbox with that. So that way, if you choose to do it, I'll see it in there. If you choose not to, I don't care, you know, that's your prerogative. So let's go through an actual computation for the two-dimensional case, because that's more practical. We can do that in class. But yeah, what I'll probably do is I'll create a PDF with the instructions for that, and then I'll upload that to the course shell. Okay, this is going to be sample. And you guys know when I do special examples in class that they're really special because I think that they're a lot of fun, and we all know it. You can think of when I think something that's fun, how great. Okay, so and when we're transforming the polar transformation, okay, let's talk about that. The polar transformation from Cartesian rectangular to the polar, and so t is given by x is equal to some function of r and theta, and y is given as some function as h of r and theta. Now, we happen to know what those rules are because it's polar. And so we can say, okay, well, this is going to be t defined by x equals what?
R cosine theta.
And then the y will be given by,
R sine theta.
if you guys mix up the cosine and sine, I think my heart will break so hard. I won't be able to sleep for days. Like, wow, how hard did I fail my students that they thought x was with sine theta? Okay.
Considering you have to do that in engineering.
Yeah, consider that you have to conceptualize so many classes. Okay, but everyone got it. So here's the thing, we need to figure out essentially to show that we can change the variables and end up with recall. And everybody can say this very confidently. Convince me that you know this, okay? Polar dA is equal to what?
RDR d theta.
So what is the Jacobian supposed to turn out to be then?
R.
So that's what we're looking for. This is gonna be the Jacobian.
Sorry, bro.
So we can find the Jacobian from the formula. So the Jacobian r theta, right, is d xy and partial r theta. Right? I personally enjoy using the subscript notation here just because it's way less cluttered, makes it easier to think. So again, the top of these are the rows. So the x and the y are the rows, and then the r and the theta, those are gonna be the columns, right? So I know that this is gonna be x's, I know that these are gonna be y's. And the reason I like this notation is because you can just put those in, and then you can do the columns. It's really, really nice. So now I know that the columns are r and theta. So these are the r's, these are the thetas. Boom. You don't need to memorize anything. You just got to recognize that. Did everyone see how that worked? In fact, it's important enough, I'll do it again. So, erase. Okay, 2x2 determinant. The variables on top, are those the rows or the columns?
Rows.
Rows, okay, so x's and y's. And the bottom, those are the columns. So r theta. And we know that this notation says x partial derivative with respect to r, y partial derivative with respect to r, et cetera, right? That makes sense.
Yes.
Can you do that? Can you remember that? And if you can't practice it, even if you can't practice it, again, repetition legitimizes. So make sure you do it. Okay, now the temptation here is to just slam everything in, but then the algebra can get kind of disgusting. So before we start computing everything, I know that when I compute this, it's going to be xr times y theta. These are the ones that are going to get paired together. And then the x theta and the yr are going to get paired together. We subtract those, so x theta yr. So I'm going to leave this as is. I'm going to plug into this, and then I can on separately on scratch paper figure out what those partial derivatives are. So I can make my little list. I'm going to need to know what xr is. Here's x, and if I differentiate this equation that we have with respect to r being the variable, yeah, this is times theta. Okay, and then x with respect to theta. So now let's do this one again, but now this time theta is the variable, r is constant.
We have r sine theta.
Good, minus r. If you forget the change of the adding the minus sign from cosine, just break my heart. I'll be so sad. Okay, y with respect to r, right? We're doing y differentiating with respect to the variable r, y theta, and exactly, because that's the variable, it's sine goes to cosine, so r cosine theta. Okay, so do you see how simple hard problems can be if you're organized? So organize your work, show your work. And then you won't make silly mistakes. Here's why people make silly mistakes, because in these determinants, you subtract this stuff. And the moment you throw in things with negative signs, you know, all records breaks loose, because it's like, not only that, it's like people will forget that cosine goes to minus, and they'll also forget that the distributive law exists. And so it just, this whole mashup of algebraic nonsense. And so just show your work, separate everything out. Don't try to do it in your head. Okay, xr is what?
Cosine theta.
Okay, so we have cosine theta. What are we multiplying x bar by? Yeah, y theta. What is y theta?
R cosine theta. R cosine theta.
Okay, so minus what's x theta?
Negative r sine theta.
Okay, and what are we multiplying x theta by? Okay, what is yr?
Sine theta.
And as far as I'm concerned, this gives you r cosine squared theta minus minus, so plus r sine squared theta. And if you factor out the r, You get r times cosine squared theta plus sine squared theta. What is cosine squared sine squared give you? One r times
Whoa.
one is
You.
r. So polar dA is what?
RD theta.
R. The RD
Theta.
theta. Yeah,
Ah,
that's cool.
very cool.
It's so cool. Man, I love this stuff. It's so cool. Yeah. Okay, so here's how this is gonna work. I'm going to make a PDF. And it's basically going to say something like, okay, you're going to need to know your transformation equations for spherical coordinates, right? I'm not gonna hand teach you that. If you haven't had it memorized by now, well, then you're automatically failing an entire question on the exam on Monday, so memorize it. And then put together the Jacobian in 3 dimensions. Is it gonna be a 2x2 determinant? No, but can you build it exactly the same way? Yes, build it exactly the same way. Now, this is not the formula for a 2x2 determinant. We're going to need to remember how a 3x3 determinant works. There's 2 valid methods that I'll accept. Okay, I'm not going to tell you what those are, but there are 2 valid methods that I'll accept for that. Just separate your work, show what those partial derivatives are. Don't try to smash all the stuff inside of this. I mean, you can, I just won't read it and I'll look at your final answer, and if it's wrong, I don't care. It's a 0, okay? Do your work separately, okay? Make sure it's correct. Do your algebra patiently, do it correctly. Show every single step. I don't want to see your mental work, okay? The point of a verification is that you're demonstrating to me, you're convince me that you actually know why it's true. Okay, so don't give me something that I could have gotten by just throwing it into ChatGPT. Okay, convince me that you know the reasoning behind something that gets you to the rho squared sine phi. If you can do that, upload that with the next lab, not the one that's due this Friday, obviously, the one after the exam. And yeah, that'll probably be worth 10 points. So yeah, 10 points.
The Jacobian method now, I'm gonna, not exactly, but it will be the Bronx multiplier, whereas the Bronx multiplier focuses on function. And this one is more about 2.
Okay.
With that,
It's I see what you're saying. So analogously, and the concept of when you're looking at you're comparing 2 things by a matter of scaling. Sure, but there is the contextual stuff is different enough. In the context of Lagrange multipliers, what you've done is you've taken a surface and you've specifically traced that like a roller coaster curve or hiking trail or whatever. You've constrained an optimization problem. Whereas here, we don't really care about that constraint. We're simply saying on a region, I can change the variables and just make sure I'm appropriately scaling. So I wouldn't liken the 2. So if you're trying to memorize it, don't liken the 2. But yes, what you're recognizing is that it's this idea that you can scale to adjust magnitude. But that's the only similarity really that it's worth memorizing, I guess. Yeah, but good question. Anything else?
The definition says in the UVW plane, but isn't a plane only 2 dimensions?
If it's a plane, that was a mistake. Should be space in 3 dimensions. Yeah, sorry. Okay, any other questions? Okay, I will see you on Friday. We'll cover some exam review. Your lab 6 will be due on Friday at midnight. And then exam Monday.
Dr. Miller, do you want our